I was having trouble because PowerPoint likes to light up both screens and it doesn't work very well with Zoom in that mode.
Okay.
Okay, so this is the agenda uh, for those. I think everybody has seen our nice new building. The the precision time and frequency system is right behind the window on the far left. So time and frequency are often misunderstood, and that's for good reason. Uh, Time and frequency are very closely related, uh, and you generally have some sort of an oscillator. That oscillator might be uh, wheels and pendulums, or crystals, or cavities, or atomic clocks, or for that matter, pulsars are very good oscillators, some of them anyway. And if you have an oscillator, it will define some frequency that it's particularly good at. Um, and that frequency can be integrated to create time. That integration can be, again, gears, counters, or whatever. And so time is based on some oscillation of some level of precision. Now, I was going to put up a really nice set of slides saying, what do we need at Haswell? What does DSES need? And the reality is, I haven't had time to sort all that out yet, and you'll see why later in the slides. I will get it sorted out, but right now we don't know. But we're pretty sure that for a variety of different tasks we have, we probably need better precision in both time and frequency than we have had up till now. So instead of telling you what DSES needs, I thought I'd give you an idea of how you develop these requirements. So if I were at a NASA VLBI site or any other VLBI site around the world, I might ask the same question. In those cases, they have somewhat more stringent requirements than we are going to have, but not always. And in this case, for example, number one, we were we had asked the various sites and the correlators for those sites what they needed, and they said, well, we need about 10 degrees of signal coherence for 1,000 seconds at 10 gigahertz. Uh, so, and there are two different sites, or more than two different sites, at different places in the world. And so they need oscillators that are about 2.8 times 10 to the minus 15th um, at 1,000 seconds. Now, DSES doesn't quite need that, but keep in mind the little bullet number one, because we're going to see where all this falls in a moment. And if you and this is actually one of the or it's actually a VGOS uh, antenna, which is the replacement or upgrade for VLBI at Goddard Space Flight Center. And just to show you what their antennas look like, they're actually smaller. The new ones are smaller than ours, but they're more expensive anyway. So there's the VOBI and VGOS systems are used for two different things. Radio astronomy is one of them, but geodesy is the other, which is 1/over radio astronomy. What do I mean by that? Well, 1/over radio astronomy is measure the phase center of the antenna to about 1 centimeter of accuracy so that we can measure the movement of the plates of the Earth, plate tectonic movements. And this is a geodetic requirement for that purpose. And in this case, the accuracy needed from the oscillators that manage the site is about 3.5 times 10 to the minus 16th at 1 day. Now imagine your crystal oscillator in your ham shack at 1 day at that precision. That's quite heavy duty. Here's a few more requirements for examples that give us bullets number 3 and 4. And again, we're seeing some fairly significant requirements. Now, we're going to have requirements not quite this stringent, but some of the things we're doing with pulsar measurements and other things would benefit significantly by having good oscillators like these. So in this case, they're saying, for example, if you have a few days of inactivity and then you start picking up the recording again of pulsars in this case, when I first started working on this, we were recording data onto mag tape. The mag tape that you used to see on big IBM computers back in the good old days, except that they had modified the recording mechanism to do a helical recording, and they were getting 16 megabits per second recording rates on the tape. And if you turned it off for a few days and turned it back on again and expected it to work, and your oscillator had to be 5 times 10 to the minus 14th accuracy after 10 to the 6th seconds, a few days. Nowadays, the recording rates are much higher. They're not 16 megabits per second, they're 8 gigabits per second. And they don't record the mag tape anymore, but that's a long story. But in any case, today, they need 2 orders of magnitude better oscillators for only 1 day of inactivity. So things get more serious and requirements get tighter as the expectations of these sites grow. And we, I think, at DSES can expect a similar thing in the future as our requirement, as our desires to do more and more challenging things grow over time, like if we did interferometry or if we do some new fancy pulsar work or whatever, our requirements are going to grow also. There's also the issue of time. In the case of VLBI, VLBI actually is the first order definition of UT1, which is one of the time standards of the world. And it is it is required to have accuracy, not just precision, that's around better than a microsecond in absolute recognition of what time is it. And the long-term behavior of their oscillator has to be measured with precisions on the order of 10 nanoseconds. Well, all of this is achieved for them by looking at oscillators. These are only a fraction of the oscillators, but I didn't want the chart to get too messy. These show that every oscillator has a noise at a, we'll call it instantaneous noise. This chart starts at 1/10 of a second. Actually, most of us don't start measuring oscillators till 1 second. We measure every second to see how good our oscillators are and compare those oscillators against some known source that's much better than our oscillators. And you get these charts called Allen deviation, which is just a measure of the frequency stability of your oscillator. So if you have a TCXO, that's the brown line up on the top. You thought that was pretty good. That's what's in your modern ham radio rig, for instance. They use TCXOs. And you'll see that it gets, as you integrate over time, it gets better out to about 10 seconds, and then it starts getting worse. And if you look at other kinds of oscillators, ovenized oscillators, and so forth, they get better, they start better, they are the best at, say, 100 seconds, or perhaps 1,000 seconds, or even 10,000 seconds, is where they're the best. But in all cases, the oscillators, by definition, are not perfect. Now, the exception is that purple line running in a fairly straight line that gets better and better and better and never gets worse, like the oscillators. Well, that is a GPS signal, not a GPS disciplined oscillator, but a GPS signal. The 1 PPS or whatever that's coming out of that GPS receiver. And why does it always get better? Because it's being steered. Every satellite in the GPS constellation is being steered and being corrected against UT1 by a closed loop system of USNO and Schriver Air Force Base, and it's very complicated, but it's constantly being steered to the correct time. So the longer you integrate, the better it is, except for that purple shaded area called diurnal ionosphere, and that is a particularly nasty problem because the GPS signals are correct, but the ionosphere is distorting the GPS signals, and that can create a problem for a GPS disciplined oscillator. So there is a chart here on GPS disciplined oscillator that shows an oscillator. Let's see, where did it go? It's not where it's supposed to be. Anyway, a GPS disciplined oscillator will get better and better and then start getting worse, but as it gets close to the purple line, will then start going down and following the purple line down. And the curve that it follows depends on which kind of oscillator you started with. So GPS disciplined oscillators are very commonly used in situations like we have, but we're not going to do that. Now, the oscillator we're going to use is the green line. That's why it's a little fatter. That's a typical rubidium standard free-running oscillator, not steered to GPS. And you'll see that its best performance is over integration times that are in the neighborhood of, say, 1,000-ish seconds. The requirements that I just talked about are the bubbles here, 1, 2, 3, and 4, and you'll see that no oscillator, including GPS and GPS disciplined oscillators, even comes close. So the only thing that meets those requirements is the red line, and that's a hydrogen maser, and I should have been more precise. It's a passive hydrogen maser. These have been getting, fortunately, have been getting less and less expensive over time. So maybe one of these days, DSES will be able to raise the funds for a hydrogen maser. But at the moment, I think the $400,000 to $600,000 a piece cost is a little bit high for our budget. So we will not be meeting those requirements that VLBI and VGOS are required to meet. Now, there's also the issue I mentioned earlier about absolute time. What time is it, and why do you care? Well, for both DSES and VGOS and VLBI, the primary need for knowing what time it is to be able to point the dish at a star or some other object in space. It's one thing to say you've got highly precise steering mechanism, but if your clock is wrong, you'll still point in the wrong place. We need sidereal time to point antennas. But that's okay. The new time and frequency system generates that kind of time as well as standard mountain time. And if we know what time it is, then we know the position of the Earth with respect to the elements out in the sky. And that makes data analysis a lot easier also. And the footnote there is mention of what all this means to pulsar work in Dan Lane's pulsar talk from last week, which I just put up on the website today. So if you're interested in pulsar work from DSES, part 1 of the training course is now available on our website under the science banner. And these things are definitely related. So these are some things extracted from Dan's talk last week. And I'm not going to go into detail about this, but I will say that pulsars are received by our antenna as pulses of radio waves. They're actually putting out continuous waves from neutron stars, but the stars are rotating and they're putting out waves in 2 directions, and those, while the star is rotating, will sweep across our dish, and so what we will get are these pulses, and if we have precision time and frequency, then our ability to extract those pulses from background noise is significantly enhanced, as well as our ability to measure what kind of a pulsar it is, what it's doing. Is it a single pulse, double pulse? And we can the more accurately we can measure all the characteristics of these pulses that we get from the neutron star, the more we can tell you about the characteristics of that star and whether, in fact, if it's a star that has been detected before, we can compare our results with those of the professionals. And the more accurate our timing and frequency is, the better job we can do at that. So for advanced radio astronomy, we need precision, frequency standard, and station timing. If you start getting really serious, for instance, if we wanted to share data and correlate data with one of our sister sites in Europe or Australia or someplace, then we would have to not only have good frequency standard and time standard in our control room, but we would also need to have precise measurement of the delay, the signal delays for all of our cables, whether they're coax cables or otherwise. All of the delays in the system, the group delays in our amplifiers, everything would have to be measured and categorized, and all of these measurements, and that includes the precision time and frequency system, which is relying on a calibration from a GPS source, would also need to have a precise measurement of the group delay in its antenna and the delays on the coax to the GPS receiver and the internal group delays in the receivers. So both the signals and the calibration system, you would have to document and instrument these delays in the system so they can all be taken out when you're doing your data analysis. Now, right now, we're just starting with first bullet, and that's it. But as we get more and more serious about the precision of our measurements for pulsar work or anything else, we're going to want to look at more of the system. Now, this chart is not technically correct. It's sort of generic. It's more or less a chart of what we did for Artemis 2. I think it's accurate for Artemis 2. It's not entirely clear for any particular projects we might do, which components will be there or not be there, but this is what we can currently do. And so what anyone who paid close attention to Artemis 2 knows is that we have an antenna with a feed. We had polarity control capability. We didn't use it, but we had it. We have a low noise amplifier as close as possible to the feed of the antenna. And then we had a splitter, and the splitter sent half of the signal to an software-defined radio, which was also located near the feed in the antenna. And the control computer, which was also in the antenna that managed these assets. And for that software-defined radio, we sent its results down to a logging computer. Well, actually, it was logged in the antenna, so this is a little oversimplified, but we did have the command and control from a computer in the control room. At the same time, we fed that software-defined radio with a 10 megahertz reference from the precision time, the new precision time and frequency system. The other end of the splitter sent the raw information to another SDR located in the control room, which was also fed with the same 10 megahertz. So both SDRs, whoops, that's terrible. Both SDRs were given the same reference so that their frequency measurements should have been the same. We think they were. And the SDR in the control room did pretty much the same job as the one on the antenna, and it independently reported data. And in the case of pulsar measurements, we might use one or the other of these SDRs or both. Don't know for any given measurement which way will go. It depends. But all of these things are capabilities, and you can see that the precision time and frequency system now is integrated with everything we do. So precision frequency is sent to the SDRs to make sure that their ADDs are clocking at the same rate, their internal processes and digital mixers and whatever are all running against a common reference. And the longer lines pointing down to the signal processing computers are timestamps from the precision time portion of the system that allow us to have time stamps on our data that are as good as 100 microseconds. And those are sent over Ethernet lines to the signal processing computers. And these signals are available for any other asset, including the ham radio station or any other asset we might want to synchronize time and or frequency. Yeah. So this chart is an old chart. I'm not going to go through it in great detail. What it was intended to describe to the scientists and technicians at the BLBI sites was somehow we needed a source of time, not just frequency, but time. We needed a fairly good source of time, and we knew that the only affordable means of getting good time performance was from GPS. And we knew this like 30 years ago. There were other ways to distribute time, but they became prohibitively expensive and they were not better. And as GPS has evolved, we have designed better and better receiver modules and better signals from the satellites themselves. And actually, I think what I'm saying here is still very achievable for tens of dollars. We can get real-time performance out of a GPS timing receiver for in the 10 to 30 nanosecond range. Now that sounds really good, and it is good, but as time goes on, a large portion of the 30 nanosecond errors is ionospheric scintillation, and we're going to get rid of that too as we move from L1 receivers to L1, L5 receivers, or in the interim L1, L2 receivers, but either way, dual frequency receivers that can compensate dynamically for ionospheric fluctuations. And we have such a receiver on site, but it's not accessible to our control system. That's the system that we have installed for the University of Texas down near the bunker. That has a dual frequency antenna and a dual frequency, I think it's an F9 or an F10 receiver, I forgot which. But we will be doing those things in the future here too. But right now we don't need better than this. And this just goes through the process of, in order to get good time from GPS, the GPS receiver must be stationary and the location of the receiver must be surveyed to within a few meters, which is not a super good survey, but it has to be surveyed at least that good. And because of the diurnal nature of ionospheric delays, you should survey for about 2 days if you really want to get a decent survey. And we've already done that at the DSES. The location that you get from a GPS receiver is not where the receiver is, by the way. It's the phase center of the antenna it's connected to. Right now, the antenna we're using for the time and frequency system is not where I would like it to be. It's just attached to the rain gutter in the building, but that's okay. It's not going to affect the precision, time, and frequency, but it does give us latitude, longitude, and altitude. That's where the antenna is. And what we really would like for science work is the latitude, longitude, and altitude of the phase center of the 60-foot dish. That's where I'd really like the antenna to be. And maybe one of these days we'll get around to doing that. We do have a GPS receiver up there with an antenna up there sometimes, but it's part of some packages that we have at the feed and not part of other packages. So we'll have to see about that over time. If we can integrate the two systems, that would make me a lot happier. And then we have, well, I'm going to show you a block diagram here in a moment, but we also have to be sure that the GPS is and the atomic clock are connected to a time interval counter in the correct way and with the correct offsets to make the whole system work properly. And then we take readings from the GPS and the time interval counter over, well, this says 5 minutes. We actually take much longer term readings. Now, we do not lock the rubidium to GPS. Most of the oscillators you've seen, whether they're rubidiums or galvanized oscillators and so forth, and there is another one in the control room which do lock to GPS, and we don't do that because we don't want the frequency, our precision frequency, to be pulled off frequency by the atmospheric scintillation, which affects the GPS. And also, there's different kinds of GPS integration, but raw GPS has a tendency to have higher noise in real time, and they provide you with the post-processing to minimize that noise in post-processing, but that means a really good steered oscillator is expensive. They're not they're not they're not trivial and they're not cheap. And even when you use all the mathematics you can to make a steered oscillator the best it can be, it still gets pulled off frequency. And I'm going to show you exactly what I'm talking about in a chart here in a moment. Our approach is to let the rubidium run free and then calibrate it. Make sure that we check its calibration routinely and that during measurement periods of whatever we're measuring, pulsars or satellites or whatever, we do not touch it no matter what. What we do instead is we measure it. We measure the performance of the rubidium over the period of our measurement time, and then we publish the results showing exactly what the rubidium's frequency error is, so that we'll know, is it important? And if it is important, we can actually mathematically remove that error in the post-processing of our pulsar or satellite data. So we can get very high precision. Now this is the rack containing the time and frequency system. Everything in the right-hand side rack and the monitor and keyboard and mouse are the time and frequency system. And just to go through it quickly, on top we have an oscilloscope that comes in handy sometimes. Then next thing down is the Hewlett-Packard HP 5065 rubidium. This is not the tiny little rubidiums that you can buy on eBay. This is the real deal. Probably the best rubidium ever manufactured. The new ones are really nice, and there's a number of companies that are making new high-performance rubidiums. None of them are better than this one. Below that is our time interval counter, which is a Hewlett-Packard, in this case, a 53131, which is good enough for what we're doing now. I'd much prefer to have a higher performance time interval counter, but for what we're doing, this is good enough. Below that is, in this rack, is a GPS receiver, which it was specifically designed for this purpose and was calibrated. This individual receiver was calibrated at USNO master site for the primary time and frequency for all of DoD. Below that is a distribution amplifier, which we use to distribute the frequency coming out of the, well, actually, what the frequency that comes out of this rubidium is 5 megahertz. And buried on a shelf that down here below the distribution amplifier is a very high performance, low noise, 5 to 10 megahertz multiplier. And that multiplier then feeds this distribution amplifier, which has 2 banks of 8 outputs. So we can drive as many as 16 10 megahertz clients from here. Then we on this shelf we also have uh, a power over Ethernet switch, and it is connected to our computer, which is under the shelf down here. And it's also connected to a custom made, you see this little dot of light in here on the shelf. That's a small computer which has custom software, and it is an NTP server that is connected to the GPS, and it is our time source, and it goes through the switch to any asset on the local area network at Haswell that chooses to get its time from that fixed IP address in the LAN. And for those who do, they get about 100 microseconds accuracy in the time that drives these various computers. There's also, I mentioned earlier, a GPS lock time and frequency reference that has been on site for, I think, 7 years now. And that is also available as a backup to this system. And every item here has been donated by DSES members. Now, this is the block diagram of the time and frequency rack that I just described. It is based on this rubidium standard, which outputs 1 pulse per second and 5 megahertz. The 5 megahertz is doubled to 10 thanks to Ray, and that goes to a distribution amp that feeds coax cables to equipment in the control room and up on the antenna feed. The 1 PPS feeds a counter, which is also fed by a GPS receiver that has an outside antenna. And this counter produces the difference in time between these two pulses. And we don't actually care what the difference is. What we care is what the drift is. How stable are these relative to each other? The counter then every second sends data to a computer, and the CNS clock, the GPS receiver, also sends serial data on the from the GPS to that same computer. Those data streams are combined, and using a software called TAC32, which creates log files on the computer every day, 365 days a year, every second is recorded. And and then the CNS clock, the GPS receiver, also feeds this custom-made NTP server, which feeds the LAN with precision time. This computer logs all the data it's logging is then sent by internet for post-process analysis, and I'll show you what that means in a moment. So this is the software that records all the data from the GPS and the from the GPS and the rubidium, and that's just the main screen. It has many screens, but the key thing is it's in position hold mode, so that it's not actually navigating, it's not generating new latitude, longitude numbers, they're all fixed. This particular this particular picture is not the Haswell picture. It's showing Eastern Daylight Time. We got to fix that. Well, actually, no, it isn't Haswell, but that's okay. This is still what the software looks like at Haswell. This is Haswell data, um, and this is a post-processed after the logs are uploaded to my lab here, I run a Python program that generates a whole series of charts. This is just one of them, but this is the most interesting for discussion today. This shows the difference in time, normalized difference in time between the two pulses, one from the rubidium, one from the GPS. In my case, here in my lab, the black line would have been perfectly straight. In the case of Haswell, this line is not straight because we don't leave the control room at a reasonably stable temperature like I do here. We just turn all the heating and air conditioning off when we leave the site, and then we turn it back on when we show up. So the rubidium is affected by temperature, as we see here. However, those changes are very small, and the average is the red line is the curve fit, and that red line is automatically computed in this box. And the bottom line is that it was at the time we measured here in March over what's that a week or two. We got better than spec. The spec on this rubidium is 1 part in 10 to the minus 12 when it's working perfectly, and 8 parts in 10 to the minus 13 is a little bit better than the specification. There's also this magnetic field thing. If you were to open the closed door on the front, there's a 100-turn trim pot called magnetic field, and it adjusts the frequency of the rubidium, and this Python program calculates whether or not you can improve the frequency error of this device by adjusting the magnetic field. And the answer in this case is no, you cannot. And the reason you cannot is the 100-turn trim pot is actually wire wound. So in a sense, it's a digital device. And over the years, I was able to find out what was the absolute minimum adjustment you could make on that 100-turn trim pot and have it actually change anything as the wiper moved from one tiny wire to the next. And it turns out it's about half of one of the of this number. 586, 500 is halfway. It's 1,000 is one direction, zero is the other, and about a half of one of the ticks on this little dial is the absolute minimum that would make any difference at all. So it's telling you don't change anything, we're fine. And then it's telling you what the error is, so that if you wanted to try to take out the error, you could. So we do have some issues with this. It's not fully automated, we found out the hard way. Power outage is our biggest concern. because and we do have a UPS, and the UPS will keep the system running through short power outages of maybe tens of minutes, but we routinely have longer power outages than that, and unfortunately, we must reset the counter and the rubidium after a power outage that exceeds the UPS's. That means a trip to Haswell. Now, it doesn't require a genius, it just requires somebody to be at Haswell, and I can talk them through these what buttons to push to do the resets. The resets are not necessary to get things up and running in terms of precision, time, and frequency, but they are necessary for the measurement that allows us to know if everything's working correctly. So this is one of the problems that we currently have, that power outages are not our friend. Uh, and this tells you sort of what you have to do. Uh, and then on a routine basis, I've been uploading the data files. I don't always do it weekly, but I do it fairly often and I run the Python program that produces the PDF reports, and I look at them to determine if there are any problems, so that if there are potential problems, that is, if the rubidium needs recalibration or repair or whatever, we can determine that without being on the site. Uh, we can find out how well things are going on a routine basis remotely. It's very simple. The NTP server, the Network Time Protocol server, can also be monitored remotely to determine if it is operating correctly. The NTP server, for example, produces status reports like this one. This is a simple command line version. And if you look at it closely, you can see what the time offsets are. And down in these charts at the bottom, you'll see the green line here says PPS, and it has a star next to it. And that means the PPS from the GPS receiver is what is being used to calibrate the NTP time that it's serving to all of the computers on the network. And it is running at an accuracy of about a half a microsecond. That's pretty darn good. And similarly, down in the second chart, we're seeing standard deviation of about 300 nanoseconds. Uh, these are numbers that your average client computer at DSES doesn't know what to do with, but they are at least an order of magnitude better than we need, which is exactly what we want from a precision source. We can log in to the precision time system with a web browser. This is a web interface, just simply by knowing the IP address. And this is accessible for it's protected. It's not a public IP address, but there's two members right now who have access to this data. And again, it's just prettier and shows more data, and it says the same thing, that the PPS is being used, and we sort of short-circuited here. I should have made it a little bigger, but it's better than the microsecond performance. We have time uh, interval showing that we're, in the hundreds of nanoseconds of performance for time service to the computers at Haswell. This is a picture of the satellites and the sun at a particular time when I captured this picture. This is the output of one of the computers that is consuming the the data from the time source, and it is using the local area network address of the NTP server, and that is showing very high performance again at the consumer. This consumer is a Linux machine, so it's a little bit better than your average Windows machine. And it's showing that the server that it's getting data from is a Stratum 1 server, which is the highest level of performance server there is. And it has two backup sources of time that it looks at for sanity checks. These are USNO time servers at Shriver Space Force Base. And so we look at those to see, uh, is there sanity here? Are we within, fractions of a second of what we're actually getting from our local server? And the answer is yes, everything is looking good. And again, we have all this data that is available. And remember, this is client data. This is what it looks like in a computer that's taking advantage of our precision time system. Now, I mentioned that the receiver at Haswell is a special receiver. I just threw this in for fun. That receiver was calibrated in 2002, so it's not a new design, by myself. And we had 4 receivers at the time and 4 counters and 4 software logging programs and a computer logging all the data from all 4 of these. And this is in a hallway uh, right behind a rack full of hydrogen maser atomic clocks, which were providing, in this case, you don't see any rubidium, the master clock going into all of these counters through this pulse distribution amplifier was the hydrogen maser ensemble pulse per second. And they don't get any better than that. And so I have one of these receivers here, and Haswell now has another one, and the other 2, the 4th one or the 5th one wasn't running. The other 2 are not available at the moment. I hope one day to get them back from a customer that has them. So I'd like to offer thanks to all of those people who helped build this time and frequency system. Again, the equipment was donated, the labor was donated, everything was built by us, by the people on this chart in January. Particular note is Art Seppin of Synergy Systems, who has joined DSES. He's the president of Synergy Systems. he donated the rubidium, the time interval counter, the computer, and the UPS and other equipment. And he not only donated it, but he drove it here to Haswell from San Diego in his son's uh, minivan. So that took, I think, 4 or 5 days of travel time and a few days of vacation time, and I took him out to Haswell. Special thanks to Art, but and also uh, Daryl, my son, put in a huge amount of time on the NTP server. He designed it and built it. The frequency doubler was a very long and involved process. Ray did all of the real work, and Ray and I worked together to measure the performance. It was not our first design, it was our best design that ultimately went out there. And uh, so that's that's the end of the presentation. I would point out this picture here is where I teach a course in precision time and frequency for VLBI. This was I actually was there when this was happening. This was uh, over 10 years ago, 2013, when we took the 120-foot diameter dish out from under the radome and demolished it and put in a new 120-foot dish that the old dish was good for 10 gigahertz and the new one is good for 120 gigahertz. And it's all back together again and working nicely. The new one was being built in the building over here, and this crane had just taken the the top off and then taken the dish out, and this down here below it is the dish. And they had to demolish the dish first, and then they picked up the building and put it over here and picked up the new dish from in here and dropped it on the pedestal. They used the same pedestal, and then put the radome back together again. So I have a lot of fun, uh, and when I do go up there to teach, my classroom is just below the dish in this building here, uh, and it's today. This is every 2 years, and this is my off year. I was there last year. A lot of fun. I love being at real sites, and I tell them all about DSES when I'm there and try to get some ideas on what we can do affordably from the professionals at a place like this. Anyhow, that's the end. Any questions? I don't know
Yeah,
how I did on time. I wanted to keep this down to an hour, and I did not do that, but I tried.
you did pretty good, Rick. I had a question. Do you have any idea how much power the full complement of equipment draws on a grid?
Guess I don't know. I think that's a good question, and I do have a meter here, a 5 pound meter that can measure that, but I'm going to guess 500 watts.
Okay. What I was thinking was, it would be possible for us to build a custom, basically UPS system. If we could put batteries, inverters, and even solar panels to run the thing continuously, so we didn't take the common power outages that we have at the site. Um, if we knew how much power it was, we could design a UPS similar to what we did with the sump pumps in times past.
Yeah, yeah, that would be very useful. this UPS is an old one, but it's a sine wave UPS, and it will accept, I believe, batteries. So if you had a whole bank of batteries charged with solar panels, you could probably connect them right to that UPS. And that way you wouldn't need another inverter.
Yeah. Yeah, and I was also thinking about just the site power usage. If it's if it's a 500 or 1,000 watts, it's also on our power bill. So, and we do
Well,
have,
that's also true. And we have certain requirements which are growing in terms of the average yearly power bill. Um, as we add things, as we try to prevent freezing pipes and this and that and the other thing, we simply uh, need to have enough income to pay for all of those things that are just sitting there working for us. But and that includes everything from the taxes to the utilities to water. Everything costs money. And all of a sudden, we went from a trailer with almost nothing required unless we were there to a building with equipment, some of which needs to be turned on all the time, uh, and and other things like we need water and we need minimal heat so water doesn't freeze. These we need donations to cover these things.
yep, yep. Okay,
So
well, just a thought. So one thing we could do is measure the power of the rack and just see what we've got, and then think about, how to augment that with batteries.
so I need to remember to bring my power meter when I go down there. I've got some equipment that I've got to swap out down there. So I do have a trip planned in the near future. And I think, whoops, didn't continue. And I'm trying to work with Ray and Dan so that I can go down there, swap equipment out, and do some pulsar measurements all in the same day because it's a long drive. You want to get the most bang for your buck while you're there.
Oh yeah. Okay. Well, great.
Hey, Rick, that was a great presentation, very helpful. Yes, that'll definitely help us on pulsars. I just have a question on this UPC that you're showing in the picture. Is it the one from the trailer that we used on Skip Crilly's equipment, or is it a different one?
I think you mean UPS
Yeah, UPS. I'm sorry.
because UPC, I don't do that. No, this UPS was donated with the rubidium from San Diego. And
Okay, all right.
I bought and installed brand new batteries in it. And
Okay,
it
great.
has huge, expensive batteries.
Yeah, all right, good. Yeah, because I found that the UPS that was in the trailer that we used to just leave on, I found it to be very noisy. It was a source of noise, so I just turned it off.
Yeah, this one is pure sine wave. We
Mhm.
need to make sure that every UPS we put in at Hasbro be pure sine wave, no cheap UPSs.
Yeah, great, thanks.
Rick, I have a question.
Yes, sir.
On the inflection on the GPS signal due to the ionosphere, do you know if that's the E layer or the F layer that causes that, or have they determined that?
Uh, I think you might find, let's see, go to the end. Where was the end? There it is. Uh, you might find, oh, that's not where it is. Where, here it is. Uh, you might find it interesting to look at this work done by Skip Creeley. Oh, shoot. every time I touch it, it goes K7ETI. He did some work on this. So I don't want to answer it and get it wrong. There are experts out there on ionospheric simulation, and I'm not one of them. But I think this might be a good place to start, looking for that answer is K7ETI's work.
Okay, I'll try and look that up and see if I can't find
Yeah,
something.
I apologize for not having a specific footnote on this chart that leads you there, but I don't think it's that hard to find.
Thank you.
Any other questions?
That was an awesome presentation, Rick. I really enjoyed it. It's even I could understand it, which is scary. So
Oh, well, now I did try to take out a lot of the equations in the science that is in my standard. My standard presentation's an hour and 45 minutes, and it has equations in it.
well, I'm sure that's riveting.
Well, I'll tell you what, when I the last time I was there a year ago, and I put on the master presentation, I got to the end and all those PDF files that I develop when I do the data analysis here. I have, by the way, every second of data from one of the space telescopes, one of the VLBI space telescopes for the last 10 years. And I had done an analysis of their performance, and it was pitiful, absolutely pitiful. And I put it up anyway. And I said, I don't know what's going on with the Western Telescope's hydrogen maser, but this is not acceptable. And all of a sudden, hands go up all over the place. And turns out that they were using the NR maser, which was the original handmade hydrogen masers that are also in use at Koki Park in Hawaii and a couple of other places. And they've lost all of the people who knew anything about them, and they lost all the documentation, and now they're afraid to adjust them. So instead, they use my system to measure the performance and send those performance parameters in with their data to the correlator instead of trying to fix the maser because nobody knows how to fix them anymore.
We'll take it.
By the way, I saw 5 of those NR masers and I said, can DSES have one of those? And they said, oh, no, 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 no. Those are for spare parts.
Oh my God.
They're
Well,
trying to keep them running as long as they can.
sounds pretty cool. Well,
Hey,
thanks,
hey,
Rick, for everything
Rick,
you've done. And I'm sure if people have additional questions, they can send those directly to you. And
Well, yeah. And I would like to announce here, because not everybody has seen my email, there is a new web page on our web server today. And that new web page is under the science banner, and it's called training. And right now, it has all the materials from last week's phase 1 training session for pulsar work. And it's in 3 basic phases. Phase 1, which is up on the page now, was planning. We don't go to Haswell without planning what we're going to do, because that's a lot of work right there. And then we're going to have 1 or more sessions on execution. What do you do when you're at Haswell? And then we're going to have sessions on post-processing and data analysis for pulsars. And all of it is going to be up there. So anybody who wants to actually look for pulsars and have the excitement of actually seeing them and finding them, which often is an exercise in below the noise work. This is not trivial stuff. And for those who want to participate, we will have captured all of that training, and anyone in the future can look at those training sessions and talk to people who've been trained and participate either on site or remotely. It won't all have to be on site. So we're pretty excited about that training exercise.
Just so everyone knows, the website is www.dses.science.
Yeah, I've never heard of that science before, but there you go. It really is.
Rick, this is Adrian. I have a question.
Yes, sir.
Yeah, I'm aware, for example, the interferometry data that was utilized by the EHT, the Event Horizon Telescope project, where they were visualizing the black holes in the Milky Way and other
Yes.
galaxies. That information essentially was recorded and then sent by disk to a central location where that was essentially the data was analyzed. So I was just curious if DSES has any collaboration for interferometric uh, collaboration, say with some of the sites like Stockholm or something in Europe. Is that how you would handle the information that would then be assembled, that would be analyzed at some centralized location to be recorded on tape?
In a general sense, that yes. And specifically, what the Event Horizon Telescope used my equipment, the same equipment that the derivative of which is now in Haswell. I'd like to just put in that plug. I
That's
met
fantastic.
I met some of the Event Horizon people before it actually happened at Haystack Observatory and worked with them on that project as well. The method they used was almost identical to VLBI. They had hydrogen masers at all the sites. They had CNS clocks and time interval counters and all the stuff I just described at the sites, monitoring the hydrogen masers and measuring their offsets. And that included Mexico and all over the place. And all of the data was sent back to that site I just showed you at Haystack Observatory, where they used a brand new upgraded correlator uh, for the correlation of the Event Horizon Telescope data. So how would we do it if we were to do it with our European or Australian partners? Very much the same, except we can't gather as much data as they did. And when they said they put it on disks, those disks were racks of equipment. They were racks of disks. And when you put over, I've got pictures, but I can't find them quickly enough to show you right now of the correlator. But half of the correlator is those racks that they send in full of disks. And when you put them all together, it's well over a petabyte of data. And no, we're not going to do that. But if we were to do correlation, we would do it the same way, just on a smaller scale. We would need to send data to a correlator, whether it's here or in Europe. Uh, we all there are machines available. I have one here that can do that kind of work. And then the correlators just have to work a lot harder and a lot longer than the one at Haystack, because we don't have the $10 million to build one like that.
Oh, that's fantastic. And another question. Again, I know the EHT utilize like gosh hundreds of gigahertz type observation frequencies, 200 whatever. And so I'm just curious, since obviously DSES will not be observing at 200 gigahertz. Does that offer any advantage of being of observations being done at a lower frequency rather than at those very high frequencies in terms of data gathering?
If you're looking for a black hole, which is something I think would be a little difficult for us to do, but if you were to do that, the closest black hole is the one in our galaxy. And to see it, you have to look through the dust of the galaxy. So you pick frequencies that are good at that. And you also pick frequencies that are good at getting through the ionosphere. No, it's not 200 gigahertz. That's it, what they will do is they'll look at bands that are 100 or 200 megahertz wide, and they'll look at maybe 4 bands at a time between 2 gigahertz and 14 gigahertz. And the choice of the 4 bands is different at each site based on avoidance of RFI. And then so it gets very complicated. But no, it's typically not. I don't remember for Event Horizon Telescope exactly what the highest band was. VLBI and VGOS are limited to about 14 or 15 gigahertz, even though the antennas can do higher, because that's what's practical for pulsar work. I'd have to look it up for EHT to see what they did.
Well, I had looked through some of their information and the frequencies that I was able to because I was specifically looking at that and some of the information that I found was stating that the BLB interferometry was done at 230 gigahertz and that they're actually pushing up to 345 gigahertz to have a better resolution of the actual black holes that they're looking at. So that's why I was curious as to
Well,
if there
I'm
was any
trying to
advantage
think
to
of
that.
the dishes that I know they used. I didn't think they had the capability of going up that high. But I don't know everything.
Yeah, I think that the lowest frequency they stated was 86 gigahertz for spectral index mapping and the scattering mitigation. I think is what they stated on some of the information that I was looking at. Anyway, I was just curious whether that offered any greater difficulty if you were trying to do that kind of data logging at those higher frequencies. Anyway, yeah, thanks.
When the dish at Haystack 120-foot dish was upgraded to 120 gigahertz, that was, oh God, they told me how much that cost, but it was well over $100 million. So to get it up to get a big dish up to even higher frequencies, I don't know. I have to look into it.
Okay, thanks a lot. Appreciate it.
Okay, well, thank you very much, everyone, for joining us tonight, and a special thanks goes to Rick for putting this all
there was a
together.
question I didn't answer. Floyd
Okay, go
asked, are there other masers than hydrogen available? There are all kinds of things like that in the science labs, but what I'm seeing as practical time source or frequency sources, oscillators that are better than hydrogen masers, they tend to be categorized as fountains, and like the mercury fountain. Well, oddly enough, coming back to the good old days, one of the most recent fountains that has had extremely good performance at affordable, only a few $1 million, is a rubidium fountain, not a rubidium like I have. So I don't know of any other masers. That doesn't mean they don't exist, but fountains exist in a number of different elemental states.
Great. Thanks again, Rick. And we will, I'm sure this will be something we'll be keeping an eye on. Lots of good work there, Rick. Thank you so much.
Thank you.
Thanks for the team that helped you as well. All right, folks. Thanks again, and keep looking at your emails. We got some more interesting stuff coming up. And on May the 9th, Megan started at the beginning of this call that she's organizing a cleanup site. So there'll be lots of folks down at the Hadwell site on May the 9th. All the best, and we'll see you later. I'll be posting this, by the way, to our YouTube channel. Actually, Bill Thomas will tomorrow morning, and so hopefully you can get another look at this again. All right. Good night, everyone.
Good night. Thanks very much.